Okay, so this is podcast 3.1, our first podcast of Unit 3, although we did start a little bit of notes together in class on page 1 and this top little bit of page 2, so it might be a good idea for you to watch that if you haven't already, because those words at the top of this page especially are going to be really important as we try and learn about these next two trends. So we are going to be starting with that atomic radii stuff, and we're actually going to be starting right underneath the periodic table, and we'll write out this stuff and then go back up and make some notes in that periodic table. So let's get to it. What is this atomic radii thing? Well, first off, radii is just the plural for more than one radius. So what we're talking about here with atomic radius is the average distance from the center of the nucleus to the edge of the electron cloud. And that's really just the idea that our atoms tend to be fairly circular, and just like you can find the circle's radius by finding the distance from the center of the circle to the edge of the circle, well, if this is an atom, then this center point is the center of our nucleus, and that outer edge of our atom is the outer edge of the electron cloud. So we're just finding the radius of our atom. And just like the radius of a circle helps us understand and compare how big or how small our circles are, really when we're talking about this atomic radius thing, we're just talking about the size of our atoms. So we're going to be using the periodic table to predict what element is bigger than the others, which ones have a larger radius than the others, just based on their position in that periodic table. Now, to do that, there are going to be two different separate patterns that we pay attention to. The patterns on how our atomic radius changes as a result of our nuclear charge changing and the shielding effect. So we're going to talk about each of these properties and how they change our atomic radius separately first, and then we'll kind of put those ideas together. So, firstly, remember that our nuclear charge is going to be increasing as we move across a row on the periodic table. That means that we have more and more protons in the nucleus of our atom, and they're pulling harder and harder on the outer electrons of our atom. So that's where our kind of explanation and definition here is going to start. Because we have that increasing nuclear charge as we move across a row, and because that increased charge is pulling harder on those same level of electrons, on the same row, we still have the same energy level, then that means that we have a stronger and stronger magnet pulling on those same electrons. Well, if they get pulled harder towards the nucleus, that means that they're getting closer to the nucleus. And if they're closer to the nucleus, that atomic radius is going to be decreasing. So overall, our atomic radius decreases across the rows. Now, shielding effect tells us and helps us predict what's going to happen in our columns. The shielding effect increases as we move down a column, and that's because the more energy levels we have, the more circles we have kind of around our atom. First energy level, second, third. Not only are those energy levels themselves getting larger in those higher energy levels, but those inner energy levels between the outermost ones and the nucleus are helping protect those outer electrons from that nuclear pull, from that pull of the nucleus, which means they're not held onto as tightly as the elements and the electrons that are closer. So if the electrons aren't being held as tightly, then that means that they're kind of more free to move farther away from the nucleus, which means that that atomic radius is going to be increasing as we get more and more shielding effect, as we move down the groups of the periodic table. So these are the two main ideas we need to know about atomic radius, is that it decreases as we go left to right and increases as we go down. So let's go ahead and summarize this on that periodic table. And you can kind of ignore the F block down there. We're really focused on these main group elements. And we're going to draw some arrows here on this periodic table. And I want these arrows to always point towards the elements that have the larger atomic radius. I don't want just left to right. I want them to point from smaller to larger. So we are going to draw one arrow across the top and one arrow off to the side. And if you remember what we were just saying, our atoms are getting smaller as we move from left to right in the periodic table, which means if I want to draw a horizontal arrow towards the biggest atoms in any row, it's going to be pointing to the left. I actually have that show up a lot neater here. So at any row, the larger atoms, larger atomic radius, will always be at the left of the row. And we said as that shielding increases as we go down, our atom's atomic radius also increases. So we're going to put an arrow vertically pointing down. So these are those two trends separately together on the periodic table. And if we kind of combine both of these arrows together, so it's pointing left and down on this periodic table, then that is pointing directly at francium. And francium is really important to remember for our atomic radius. This is the element, out of all of the elements on that periodic table, francium has the largest atomic radius of all of them. And that means when we're trying to work out problems and figure out of a different random set of elements which one is bigger, all we need to ask ourselves is, well, which one is closer to francium? The closer to francium that we are, the larger our atomic radius is. And this abbreviation, FR for francium, kind of sort of matches and kind of mimics that AR for atomic radius. So AR is biggest at FR is something that you're going to have to remember in the long term, because we're going to have a couple different trends, a couple different patterns to remember, and they're all going to be greatest at some different element. So AR going with FR, important to remember. Now here in these example problems at the bottom of the page, we just need to figure out in this first set which of these elements is larger. So I have FR marked on this periodic table just to help remind you closer to FR is larger. So all we've got to do at this point is find where our elements are on that periodic table, and whichever one is closer to FR has the larger atomic radius. So in this first set, that's going to have to be lithium. That's because it's closer. In this next set, that's going to be strontium, because strontium is closer. In this next set, helping you find those elements, rubidium is farther down, even though this is a completely different thing with it being in columns instead of rows. And the reason why they're different really comes down to different properties. The short answer is you don't need to know any of that stuff unless I ask you why. For most of this, it's just whichever one is closer to FR. So here, that's rubidium. This next set of questions asks you to put them in order of increasing size, which seems like a completely different type of problem, but really when it comes down to it, we still just need to find our elements, and I've highlighted them here. You do need to make sure you're careful, because sometimes we talk about increasing, sometimes it's decreasing. So each time you see this, I'd highly encourage you to write out what order you're going to write them in. What I mean by that is increasing. Most people think, oh, that means big. But we're not going to start with the big ones. Increasing means getting bigger, getting larger. So we need to start with the smallest atoms and go towards the biggest atoms to get these in the correct order. Even though I've been doing this for longer than y'all have been alive, I still write that down because it's so easy to just get these completely backwards. So if we're looking at our three elements here, if we want to start at the smallest one, that's going to be the one that is farthest away from francium. And then we're going to write them in the order, getting larger, getting closer and closer to francium. So that means we're going to be starting with CD, and then TC, and then Y. That's all there is to it. Finding our next three elements, they're right next to each other in that second column, and still going small to big for that increasing size. The farthest one away is BE, then MG, and then CA. And oh, look at that. Most people wouldn't think that I would write them in the exact order they need to be. They're always going to mix them up and guess even if they don't understand the question, but they could still already be in the right order, obviously, since it was this time. So, trust yourself in your periodic table. That's really where you get the confidence for your answers. So, this last one, I do want to see you answer on your page. Even if it's not right, I'll give you a stamp, but I will not stamp it if it is blank. So, do your best with this example. And then let's move on to talking about ionic radii. All this is, remember, ions are just atoms that have gained or lost electrons. So atomic radii and ionic radii are almost the same thing. So we're going to basically take that atomic radii definition and change it a little bit. Since atomic radii is the size of an atom, and ions are just atoms that have gained or lost electrons, ionic radii is the size of an atom that has gained or lost electrons. And depending on whether it gained or lost, it's going to be getting bigger or smaller. That's really all there is to it. So if we focus on those separately, remember that positive ions, which tend to be metals, generally lose electrons to become positive. They have to lose electrons because electrons are negative, so if they want a positive charge, they have to have less negativity. And just like if you lose weight, that makes you smaller. It makes our atoms smaller too when they lose electrons. Negative ions are the opposite. They tend to be nonmetals. They have to gain electrons in order to become negative, and gaining electrons, just like gaining weight, makes people larger, makes our atoms larger as well. So make sure you get that first definition down, but if you'd like to summarize those last two lines there, just by saying more negative equals larger, more positive equals smaller, I could see that. Because that's really all we need to keep in mind as we are looking at these different ions. In fact, I'm just going to keep the more negative equals larger, because that's what we're looking for, is our larger ionic radius for these ions. But we might need a little bit more than that, perhaps, because this first problem, A, doesn't have anything that's negative. So remember that less positive is going to be larger, just like more negative. So which one of these is less positive? Well, the positive one instead of the positive 2. Here in part B, we have a carbon with a negative 2 charge and a positive 2 charge. Well, if we want the larger one, we're going to go with the negative one. So go ahead and do the same kind of thing here with part C. You probably already have. I want to see you circle one of those to get your stamp in class, but if you're not sure of either of these answers on either of these problems that I asked you to do on your own, please let me know as I'm coming around and stamping, but pretty sure you can handle this. I trust your instincts. Just let me know what I can do to help. Hopefully this wasn't too painful.